Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is your instructor Anisa Nawaz from Department of Physics. This is our lecture number 15 from chapter number 2, Vectors and Equilibrium. In the previous lecture, we have discussed about some examples and assignments in your book related to addition of vectors by rectangular components. And in this lecture, we will learn about how to multiply a vector with a vector to get a scalar in the result. And in other words, you can say we will learn about scalar or dot product. Okay, up till now we have discussed about vector inverse or negative of a vector, in which if we were having a vector, we just have to switch the direction. That will give us negative of the vector. Then we have discussed about vector addition by head to tail rule, in which we were having two vectors. Head of the first vector was joined with the tail of second vector, and tail of first to the head of last will give us the resultant addition of the vector. Or we can do the same by parallelogram method, in which we have to draw parallel vectors of given vectors, and then the resultant, the diagonal, will give us the sum of these two vectors. And we have also discussed about vector subtraction, in which we are having two vectors, vector A and vector B, and if we have to subtract these two vectors to get the resultant, we simply have to switch the direction of B. We have to invert the direction of B and add A with minus B. Then we have also discussed about vector multiplication by a scalar. We have multiplied a vector by a scalar, in which if the scalar or simply a number, if number was positive and we were multiplying it with the vector, it was increasing the magnitude, and if the scalar or the number was negative, then it was increasing the magnitude as well as changing the direction. And we are having another method of vector multiplication, that is known as scalar or dot product, which we will discuss, and vector or cross product, which we will discuss later. Okay, so the dot product or vector product, so far we have added two vectors and multiplied a vector by a scalar. So the question is it possible to multiply two vectors so that their product is a useful quantity? Can we multiply two vectors? What is the way to multiply the vectors, and what will be the result? Either it will be a scalar or it will be a vector. That is the question. So we will check that out, that how we are going to multiply the vectors to get the resultant or the answer. So one such product is the dot product, which we consider in this section. Okay, so when two vectors are multiplied, we can obtain two types of results depending upon the physical nature of the vectors. Okay, it depends upon the physical nature of the vector, that whether the resultant is a scalar quantity or a vector quantity. What is the result, whether it is scalar or a vector? Okay, so either we will get a scalar product or we will get a vector product. If we are multiplying two vectors, then we are having a result which is a scalar. By multiplying two vectors, if we are getting a result that is a scalar, such type of product will be known as scalar or dot product. Because result is a scalar, that's why we are saying it scalar product, and we are using dot operator, that's why it is also known as dot product. And if we are multiplying two vector in such a way that the answer which is obtained is a vector quantity, then such type of multiplication is known as vector or cross product. Okay, so we are having two different ways to multiply vectors. In this lecture we will just discuss about scalar or dot product. Okay, so if you are going to define the scalar product, when a vector is multiplied by a vector and the resultant obtained is a scalar quantity, such type of vector multiplication is called scalar product. Definition is simple, that if we are going to multiply two vectors and we are getting the result which is simply a number, simply a magnitude, then such type of multiplication is known as scalar product. Vector multiplied by vector gives us a scalar. Okay, so for example, if two vectors A and B are multiplied such that their result is a scalar C, then such type of multiplication is called scalar product. We are multiplying vector A and vector B, that gives us a scalar C. This type of multiplication is known as dot product. Okay, so usually a dot is placed between two vectors to represent scalar product, therefore it is also called dot product. Okay, scalar product or dot product definition is that if we are going to multiply two vectors, we will simply get a scalar in the result. We can also write it as A dot B is equal to AB cos of theta. Okay, A dot B is equal to AB cos of theta. You can see over here vector A, vector B, which is equal to scalar A, magnitude of A, scalar B, and cosine of theta. Cosine of theta, again it is simply a number, it is having no direction, so all this value is a scalar quantity. So over here you can see that while we are multiplying these two vectors, we are not multiplying complete vectors. Okay, we are not multiplying complete vectors, we are not simply multiplying their magnitude, or we are also considering their angle, we are also considering cos of theta. This cos of theta is very important in this dot product or scalar product. Let's check it out that how it is important. Okay, so this angle theta, what is this angle theta in the relation A dot B is equal to AB cos theta? Normally if you are asked about the theta, what is theta, you say that theta is the angle from positive x-axis in the anti-clockwise direction towards the vector. That is normally the definition of theta, but this theta is different. This theta is basically angle between vector A and vector B. It is angle between vector A and vector B. Okay, and it is smaller of the angles between two vectors. If we are having two vectors, then we will check out how this is smaller of the angles, but you have to keep this in mind that theta is always smaller of the angles between two vectors. So this theta is not the angle from positive x-axis in anti-clockwise direction, it is simply the angle between vector A and vector B. Okay, so if we are going to physically interpret the definition of dot product, we can also say that the product of magnitude of one vector to the component of the second vector in the direction of first vector. How? We are saying that if we are having two vectors, vector A and vector B, and we are multiplying these two vectors, we are getting this result. You can see that we are having a vector A and we are having component of vector B, B cos theta. If you remember resolution of a vector into rectangular component, we were having two components, sin theta and cos theta. Okay, if we were resolving force into horizontal and vertical component, we were having f cos theta and f sin theta. Similarly, any vector can be resolved into horizontal and vertical component. Over here we are having complete magnitude of the vector multiplied by magnitude of component of the other vector. Which component? It is basically the horizontal component of the other vector. Okay, we are multiplying magnitude of one vector to the horizontal component of other vector. It is not necessary that I am using horizontal component of vector B. We can also use horizontal component of vector A. Both will give us same result. Whether it is A B cos theta or B A cos theta, both will give us same result. Okay, so you can see over here, if we are having two vectors, vector A and vector B, and we are going to multiply these vectors, first step is that we have to join these two vectors from the tip, from the tails. We have to join these vectors from the tail. Initially in head to tail rule, you have considered this thing that tail of the first vector, head of the first vector with the tail of second, and up to so on. But in scalar product, you have to join the tail of two vectors to a common point. If we are having any two vectors, we have to join their tails to a common point. You can see here that one angle between two vectors is this, and the other angle between two vectors could be this complete angle, but we are considering smaller of the two angles. Okay, we are considering smaller of the two angles, which is basically theta in this case. First we have to join the tails of two vectors, then we have to consider the angle which is smaller, angle between the two vectors which is smaller in magnitude, that will give us theta. Okay, so over here if we are talking about the magnitude of first vector to the component of second vector, we know that if we are going to resolve this vector b into components, so we have to draw the perpendicular, we have to drop the perpendicular from this vector on the other vector, you can see here. So this basically is the vertical component and this is the horizontal component. Okay, this is the vertical component of vector b and this is the horizontal component of vector b, but by definition we have to consider only the horizontal component of vector b. We have to multiply the magnitude of this vector a with just the horizontal component, just the horizontal component of vector b. We will not multiply complete vector b, but we will multiply vector a with the horizontal component of vector b. This is something new for you people, but this topic is very important, so you have to practice it properly. Okay, so this dot product, scalar product or vector product, these are again important from the point of view of long question as well as from the point of view of MCQs, so you have to concentrate. Okay, so over here we can define a dot b, scalar product of two vectors, which is equal to product of magnitude of first vector to the component of second vector in the direction of first vector. So what is b cos theta over here? B cos theta basically, okay, over here let's check this out. We have initially considered this that a is along x-axis. Okay, it is not necessary that a is along x-axis, it could be along any direction. Okay, and if you are going to rotate it, then it will again give you the same result. So if we are going to draw this figure in this way, we are drawing vector a in this direction and vector b in this direction, then what we will do, first we will join the tips of two vectors. We are not changing the direction, we are just joining the tips of two vectors. Okay, and we are considering the smaller of two angles between these two vectors. Then we are dropping a perpendicular from one vector on the other, and we are considering horizontal component of this vector b cos theta. Then a dot b will be equal to ab cos of theta, magnitude of this complete vector multiplied by component of other vector in the direction of first vector. So this is basically scalar product of two vector. By definition we are having a dot b is equal to ab cos of theta. Okay, what about b cos theta? You can interpret b cos theta, you can give it different names, you can give it different interpretations. You have to learn all these names. You should know that what is basically all these things, what are basically all these things. Check this out, that b cos theta can be said as horizontal component of b. Its one name could be horizontal component of b, another name could be effective component of b. Okay, b cos theta can be said as effective component of b, component of b in the direction of a, or projection of b on a. All these are the names of b cos theta. You have to remember all these names. If it is said that we are having product of one vector with horizontal component of other vector, then again if we are having product of one vector with the effective component of b. Okay, if we are having product of vector a with component of b in the direction of a, or if we are having product of vector a with projection of b on a, all these gives us the same meaning. Okay, you have to learn all these names for b cos theta. Okay, so what is the meaning of projection of vector? We have discussed this thing that b cos theta is also said as projection of b on a. So what is the meaning of this projection? Normally you say that projection means shadow. normally we take projection as a shadow. Okay, so what we have to do over here, we will simply check out over here. You can see that we are having two vectors, vector A and vector B, and we have connected these two vectors from the tips. Okay, you can see this thing that we have connected these two vectors from the tips, and we have considered smaller of the two angles as theta. Then what we will do, we will draw the projection of A. Okay, we will draw the projection. We will check out that, let's say we are having a lamp which is just above this vector A, and we are checking out the shadow of vector A on this vector B. Okay, we are checking out the shadow of vector A on vector B. So what will be the dot product over here? Complete magnitude of vector B with shadow of vector A. We have to take product of magnitude of B with the shadow of vector A. Okay, so what we will do, we will check out the projection of one vector on the other. It simply means the shadow. We are multiplying magnitude of one vector with the shadow of other vector. Okay, so we can say that dot product will be A cos theta multiplied by B. Okay, so if we are going to check out the shadow of second vector on first vector, then what will be the result? Check this out, that if we are placing the lamp just above the vector B, then what will happen? You can see the shadow of vector B on vector A. We are dropping the shadow of vector B on vector A. We will just check this out. We will check this out, that what is the projection of B on A, and we will simply multiply the magnitude of this vector A with shadow of vector B. Okay, so we can say that the scalar product is basically equal to the product of magnitude of A with the projection of vector B on A. Okay, so these are the different definitions for scalar product, but all gives us the same result. If we are going to multiply two vectors such that we are having a result which is a scalar, then we will multiply one vector with other vector in such a way that we are taking magnitude, complete magnitude of one vector and component of other vector along the direction of first vector. Okay, so we can say that the dot product says something about how parallel two vectors are. You can see over here that if these vectors are parallel to each other, if this vector is moving in this direction, its shadow will keep on increasing. So it is telling us about the how parallel two vectors are. If two vectors are more parallel, then we will having a bigger number, we will having a bigger result. Okay, so dot product or scalar product of two vectors can be thought of as the projection of one onto the direction of other. Okay, for example, if we consider the two vectors which are just perpendicular to each other, because we have discussed this thing that it is telling us that how parallel two vectors are. So these two are not at all parallel, these two vectors are just perpendicular. Now check this out, that what will happen, we will draw the projection of A on B. You can see there is no projection on B, we will be having no projection, because if you can imagine this thing that if we are standing under the sun and sun is just above us, then we will be having no shadow. Okay, just at 12 noon you can see this thing that we are having no projection. Same is the case over here. If two vectors are just perpendicular to each other, then projection of one vector on the other will be 0 and dot product will be 0. So it is telling us about how parallel two vectors are. If two vectors are parallel, then dot product will be having a bigger result. If these two vectors are perpendicular to each other, then dot product will be having 0 result. Okay, so by definition we can simply say that product of two vectors A and B, it is equal to, we can write it in either format. This representation is also for magnitude of A. Okay, we are writing it as bars with arrowhead. This is showing us the magnitude of A, and simple A is also showing us the magnitude of A. So we can write it in either ways, both are correct. A dot B is equal to magnitude of A multiplied by magnitude of B multiplied by cos of angle theta between the two, which is smaller of the two angles, and A dot B is equal to AB cos of theta. Both are giving us the same result. Okay, now if we consider examples of dot product where we are using the dot product, so one simple example is in work done. We know that work is a scalar quantity. Okay, work is a scalar quantity, so we are not putting arrowhead over here, but force and displacement are vector quantities, so we are putting arrows on force and displacement. When we are multiplying these two vectors, force and displacement, we are getting a scalar quantity. This is the example of scalar or dot product. We are taking example of work done, force into displacement. Two vectors are multiplied to get a scalar quantity. Work is having no direction, while force and distance or displacement are having directions. Okay, another example could be power. Power is a scalar quantity, so it will be having no arrowhead. It is equal to the product of force and velocity. Force is a vector as well as velocity is a vector. So again we are multiplying two vectors to get a scalar quantity. We are having numerous other examples related to this scalar or dot product. Okay, so we are having different vectors which are giving us the after multiplication they are giving us the scalar. But we say that question is that how we come to know that we have to use dot product over here? Why we can't use cross product over here? If we are having force and displacement and we are multiplying these two vectors, why we are not getting a result which is a vector? What is the reason? Let's check it out. What is the reason behind that? You can easily check this out, that when we are going to use scalar product and when we are going to use vector product. You can see over here that a boy is pulling a cart and he is applying a force over here at an angle of 30 degrees, but the cart is moving in forward direction. Displacement is along this direction. Now tell me that whether the cart is moving in the direction of force? No, it is not. So which one is the effective component of this force? You can see that this force can be resolved into two components, vertical component and horizontal component. This force is resolved into vertical component and horizontal component. You can see over here the cart is moving in this direction along the horizontal component. This vertical component is playing no role. So what will be the effective component of this force right now? That will be F cos theta. So we will simply multiply displacement with F cos theta. In this way we will get the result as a scalar. We are not using sine theta over here, we are not using its perpendicular component, we are using its horizontal component. And if these two are horizontal component, then what will happen? This is basically the effective component. Cos theta is basically the effective component because both of these are along the same direction. Displacement and F cos theta are along the same direction. Then what will happen? Theta is 0 in this case and cos of 0 is 1. We will simply get the maximum result. Work will be Ft cos of theta. Okay, so we are using horizontal component in this case because horizontal component is effective one. So whenever we are using horizontal component, we will use dot product. Keep this in mind, that when vertical component is playing no role, then we have to use dot product, and when vertical component is playing the role and horizontal component is playing no role, then cross product is used or vector product is used. Okay, consider another example. We are having a lawnmower which is moving again in this direction. Force is applied over here. Again, what is happening? Displacement is in this direction. Okay, displacement is along this direction and it is not moving in this direction. Okay, so this vertical component is having no effect, it is playing no role. So we will simply multiply displacement with F cos theta. Okay, we will simply multiply displacement with F cos theta and we will use a dot product between the two. Okay, so you can see here that if we are having a force and we are having a distance along this direction, then this green arrow, it is telling us about the displacement, and this pink one, it is basically the horizontal component of this force along the direction of displacement. So we simply have to multiply this displacement and horizontal component of force to get the dot product or scalar product. Okay, so up till now we have considered the projection of B on vector A, but either we can draw projection of B on A like this, A dot B is equal to AB cos of theta, or we can draw projection of A on B like A dot B is equal to BA cos of theta. Okay, so we can say over here we are having vector B and vector A, and we are dropping the projection of A on B, and we are getting A cos theta, horizontal component of A along the direction of B. So we will say that A dot B is equal to BA cos of theta. So we can draw either projection. Okay, so let's check it out, that how we are going to multiply two vectors by drawing the projection over there. You can see we are having two vectors, vector A and vector B, and smaller of the angle is theta. So A dot B can be written as magnitude of vector A multiplied by magnitude of vector B with cos of theta between them, and keep this in mind that theta is between 0 and pi. Theta cannot be greater than that. If we are taking theta greater than that, then it will be the bigger of angle between the two. Okay, so if we are having two vectors and we want to multiply it with scalar product, then we have to drop the projection of A on B. You can see we are having this OM, which is basically projection of A on B, projection of vector A on projection on vector B. Okay, so this is basically the effective component. If we just consider this triangle, we can simply say that OM over A, base over hypotenuse, is equal to cos theta, and cos theta can be or you can say that OM is equal to A cos theta. This horizontal component, this effective component, is basically cos component. Okay, A cos of theta. That's why we say that whenever we are using dot product, we use its horizontal component. So vector B, magnitude of vector B multiplied by A cos of theta, horizontal component of vector A. Okay, so if we are interchanging these two, we are dropping the projection of vector B on vector A, we will again get same result. Vector A, magnitude of vector A multiplied by B cos theta, both will give us the same result. Okay, so this was which we have discussed in scalar product. Okay, so if we are considering a simple example related to dot product, that if we are having vectors A and vector B, lengths 4 and 6, this is basically the magnitude of these two vectors, and the angle between them is pi by 3. Find A dot B. We have to find A dot B. So what we will do, we will simply put the formula A dot B is equal to magnitude of A multiplied by magnitude of B into cos of pi by 3. Okay, so that simply by putting the values we will get 12. Okay, so either use arrowhead over here on this A and B, or don't use these bars. Okay, simply write AB cos pi by 3 or these bars with arrowhead. Okay, that will represent the magnitude. Arrowheads are missing over here. Okay, so we will get this, simply we will get a magnitude. We will simply get a magnitude by multiplying two vectors. We will get a scalar. Okay, so if we are multiplying two non-zero vectors A and vector B, these are called perpendicular or orthogonal if the angle between them is pi by 2. We know this thing, that if two vectors are perpendicular or orthogonal to each other, then angle is pi by 2. For such vectors, what we will have, we will multiply vector A and vector B. We will get AB cos of pi by 2, and we will get 0. Resultant will be 0 because cos of pi by 2 is 0. Okay, and conversely, if it is given that A dot B is equal to 0, then we know this thing that cos of theta is 0, so these two vectors must be perpendicular. So if it is given that we are having two vectors, their dot product or scalar product is 0, then we should know this thing that these two vectors must be perpendicular to each other. Okay, keep this in mind, that whenever two vectors are perpendicular to each other, their dot product will be 0. Because they are not at all parallel to each other, so their dot product is 0. And if it is given that dot product is 0, then we should know this thing that theta must be 90 degrees. So we can say that the dot product A dot B is positive if theta is less than pi by 2. Okay, if we are putting cos theta less than pi by 2, then dot product will be positive. It means that we will check this out, that if whether two vectors are almost parallel to each other or not. Okay, their dot product will be 0 if they are perpendicular to each other, and their dot product will be negative if theta is pi by 2. So if just this value, this factor is given that dot product is positive, then you should know this thing that theta is less than pi by 2. If it is given that dot product is 0, then you should know this thing that these two vectors must be perpendicular. And if it is given that dot product is negative, then you should know this thing that theta is greater than pi by 2. Okay, you can check this out, that if we are having two vectors such that their angle is less than 90 degrees, then their dot product is positive. If two vectors are perpendicular to each other, their dot product is 0. And if two vectors are having theta greater than 90 degrees, then their dot product will be negative. Okay, you should keep this in mind. So we can simply say that dot product A dot B as measuring the extent to which A and B point in the same direction. We are just checking out that how parallel these two vectors are. Okay, so in the next lecture we will elaborate the same concept. We will discuss about characteristics of dot product in detail. Inshallah, we will discuss about different properties related to dot product. So I would like to end my lecture with this quote, that the great thing in this world is not so much where we stand as in what direction we are moving. So you should mind this thing, that in which direction you are moving. It doesn't matter that where you are standing. Keep on moving, keep on learning, keep on achieving. That is a never ending journey. Thank you so much. That was all for today's lecture.